Today we're going to start looking at special quadrilaterals. In specific, we're looking at parallelograms and the different special types of parallelograms we have. However, before I go through the properties, I want you to actually explore some of these diagrams. So you'll notice I have a link at the top of the page that I'm sharing. This link is also available on Schoology, and I want you to look at this online book. So it has basically, it's a collection of pages where it's all in an interactive program called GeoGebra, where you can actually click off the different properties and pull the shapes around, pull the corners around to see what kind of properties hold true. So please check that out first, and then come back to this video, and I'll go through the properties real quick, and we'll talk about how those shapes are related to each other. Alrighty, so hopefully as you were looking through, you found your different types of quadrilaterals. Every single one of the shapes that you looked at, everything has four sides, and that's why we call these quadrilaterals. Our prefix quad is talking about four, so we're looking at a four-sided figure. You'll also notice that everything that you looked at, everything was a convex figure, so that means all of the vertices are kind of pointing out towards the center. You didn't have anything pushing in towards the center of your shape. So for parallelograms, our biggest idea is we have opposite sides are always going to be parallel, but the side lengths of those opposite sides are always going to be equal or congruent, as will be the angles. So opposite angles are also congruent. Your diagonal segments, so if you're connecting your vertices that are across from each other, they are always going to be cut in half, aka bisected. However, your adjacent angles, so if you're looking at your figure, let me sketch a small one up here. Again, parallel sides and they're congruent. Parallel sides and they're congruent. So notice I'm using different marks for parallel, different marks for congruent. So make sure your parallel lines, when you're looking at these diagrams, you're looking for the arrows for parallel, but you're looking for the dashes for congruent. And so when it's talking about adjacent angles, again, it's looking at angles that are next to each other, kind of like when we dealt with parallel lines. So adjacent angles would be like the single dot and the double dot. Those two angles are always going to be supplementary. They're going to add to 180 degrees. So supplementary. And anytime you draw in a diagonal, which connects two opposite vertices, just like we were trying to figure out with our angles before to find our triangles, those are always going to make congruent triangles to each other. Alrighty, the second figure that you looked at was a rectangle, or one of the other types of parallelograms was a rectangle. And again, y'all have dealt with these before. So these are going to be specifically right angles in your corners, and your opposite sides are always going to be congruent. They're also always going to be parallel. And so it has everything that the parallelogram does, but the extra pieces are, well, now we have 90 degrees in the corner angles. And if I draw my diagonals in, and again, if you didn't explore this, go back to that online book to check this out. Your diagonals are always going to be congruent to each other. Now, this is not going to happen in a parallelogram. Okay, all your triangles that are made by those diagonals are all going to have two sides being equal then because of that. So when you use your diagonals, so if I draw those diagonals in, I make two pairs of isosceles triangles. Again, that won't happen in parallelograms, so rectangles are almost a special type of that kind of shape. Okay, next one you have is a rhombus. Although if you're looking at the plural of that, that's rhombi. That's why I have that in there. So again, they have all the parallelogram properties. Opposite sides are parallel, opposite sides are congruent, the diagonals bisect each other. But this, again, we have to kick it up a notch. Every single side, no matter what, is going to be congruent to all other sides. So when we see this drawn, again, it looks like a parallelogram because it is a type of parallelogram, but specifically all the sides are going to be congruent to each other. When we draw in our diagonals, and again, if I did a decent job of drawing these, or if I did a decent job of drawing this rhombus, what kind of angle does it look like those diagonals come together to make at the center? 90 degrees. Also, too, your vertex angles are always going to be cut in half. So your vertex angles are going to be bisected. Again, that doesn't happen in a normal parallelogram, only with a rhombus or anything that can be considered a rhombus. And so when we get to the most specific shape possible, and this is what you're usually thinking of with a quadrilateral, your brain naturally goes to square because it really is the most perfect kind of parallelogram. And in fact, it has every single property out there. So it has all the properties of parallelograms. So that means opposite sides are parallel, opposite sides are congruent. It has the adjacent angles are supplementary. It also has the rectangle properties. So that means all the corner angles are 90-degree angles. If you draw on your diagonals, they're congruent to each other. You make a bunch of isosceles triangles when you do that. But it also has all the properties of the rhombi. So that means it also, when you draw on your diagonals, they make a 90-degree angle in the middle. You bisect all those vertex angles as well, and all of the sides are still going to be congruent, just like a rhombus. Okay, the two extra kinds of pieces that you explored that we're not going to do as much with, but we're definitely going to come back and look at one of them. Specifically, we're looking at trapezoids. So you'll notice I kind of grouped the trapezoid pieces together. All of the parallelogram pieces are grouped together on the other side of the chart. So trapezoids specifically are only going to have one pair of parallel sides. So they may look something like this, with a set of parallel sides. However, that's really all they've got going for them. Specifically, we call those two parallel sides bases. And we're going to come back and look at why do we have two bases technically? Usually you think base is a bottom of a shape. But again, we use that because we could flip this around and either one of these sides could be considered the bottom, depending on which perspective we're taking. However, an isosceles trapezoid, we'll think of that word. Isosceles means two sides equal. So your non-parallel sides, so the things that are not the bases, those are going to be congruent. And your base angles, the guys that are on the same side or on that same parallel line, those are always going to be also congruent. So when we're thinking about an isosceles trapezoid, again, we're thinking about a very symmetric figure that's exactly the same on the left as it is on the right. So we have two parallel sides, and then we have two congruent sides. Our base angles, that would mean like on the very bottom, those two angles would be congruent, and the very top, those two angles would be congruent. And again, we're going to come back and spend a day just on trapezoids a little bit later on. So kind of file this away in the back of your brain. Okay, last shape is a kite. Now, kites are not actually tested on the geometry SOL. But if you're ever going to take the SATs or ACTs, I wanted to at least think about these values or these kinds of polygons. Kites are going to be where they have two pairs of congruent sides. So they have one pair that are adjacent to each other that are congruent and another pair adjacent to each other. And exactly the figure that you think of with kite, like flying a kite. So two pairs of adjacent sides that are congruent. Okay, and then the angle made by the diagonals, we'll think about the supports that you usually have on a kite. So if I connect my diagonals, I make a perfect right angle in the middle. So again, a type of figure that you might see in casual conversation or problems on things not your geometry SOL. Okay, so another way that we can think about this with how all of our shapes are related to each other, and you're going to look at this in the interactive practice that you're going to do right after this. Let's look at the relationship between these types of quadrilaterals. So our biggest type of figure, technically this is encompassing all quadrilaterals, but specifically we're going to be studying parallelograms. And there were three kinds of parallelograms. We had rectangles, rhombi, and squares. So our two separate ones that didn't have a whole lot in common were our rectangles and our rhombi. What was the most perfect parallelogram that had every single possible property? Well, those are our squares. And so we can think of this as a Venn diagram and think about, well, how are these related to each other? Well, a square has every single possible property. So it could technically be in the group of parallelograms, rectangles, and rhombi. Rectangles, sometimes they might be in common with a rhombus. That's going to be something that's going to be a square, but it doesn't have to be. So a rectangle, again, still has all the properties of parallelograms as part of that bigger group, but it's not necessarily going to overlap with the rhombus properties. And so if we want to actually kind of connect the other figures, we could have trapezoids off to the side, and we could have kites off to the side. And again, I don't have those in the same group as parallelogram. They're still quadrilaterals, but they don't have any of the main biggest properties of parallelograms that they need. Okay, so how we can put these ideas together? Well, is a square a parallelogram? Well, yes, it's part of that big group. Actually, let me shrink this down a bit so we can see everything at one go. So our big group parallelogram, well, yeah, a square is going to be a parallelogram every single time. It's a subset of that group. So it's always going to be a parallelogram. But is a parallelogram always going to be a square? Not always. So it's only sometimes going to be a square. So sometimes it'll have enough properties to be a square, sometimes it won't. Is a square a rectangle? Well, yeah, always. It has every single property that a rectangle needs. That subgroup of squares fits completely in that rectangle group. But if I reverse it, yeah, a rectangle is only sometimes going to be a square. Is a square a rhombus? Well, yeah, it's completely contained in that group. But is a rhombus always going to be a square? Only sometimes. Only depends on if it has all the other properties as well. So with your practice today, you're really just looking at identifying which shape is which and thinking about your basic properties. So then over the next couple lessons, we're actually going to look at each individual type of parallelogram and how we can solve problems with those. So probably going to be looking at 3 days. So one day where we're going to do parallelograms and rectangles, one day where we'll do rhombi and squares, and then we'll do another day on trapezoids and all the different things we can do with those. Let me know if you have any questions, and if not, start in on your practice.